we could draw a magnetic field, and it could look like, you guys have all seen magnetic fields that look something like this. Okay, here's a magnetic field, B. Okay. How do I draw that magnetic field if all of a sudden it turns at 90 degrees counterclockwise to us and turns into that page, into the wall? How do I draw it? If you imagine, this is how they thought of this. This is where this comes from. An arrow. Arrows look like that, don't they? What would that arrow look like if it was coming towards us? It'd look like that. Okay. What would it look like if it was going away from us? It would look like that. And so what they're saying is, if I turn this around clockwise, so bring it around and face it towards us, that it's going to look like that to us. And that's why they do these as dots, or dots with circles around them. Out of the page. That magnetic field is coming out of the page. It's uniform. Does everybody understand that? So that denotes out of the page. And that denotes into the page. And that's where it comes from. Okay. So here we have some particle with some speed v. There it is there. It might be a proton. Actually, we can work out whether it's a proton. We can work out what charge it is, but I'm not going to do that now. I'm just going to say that it could be positive or it could be negative. Later on, you're going to be able to tell how to do that using the right-hand palm rule. But anyway, so it comes in here, hits this magnetic field. Of course, there's no forces acting on it. Hits this magnetic field, there's a force acting on it, and it causes to turn in uniform circular motion until it leaves that magnetic field, and then it continues on its path. The centripetal force is provided by magnetic force Fc, of course, is equal to mv squared over r, which equals, in this case, the charge multiplied by the velocity, by its velocity, multiplied by the magnetic field that it moves in. Okay? I don't want this to look untidy either. Just so that you know that this one is for charged particles and this one is for magnetic fields. Who's heard of a free body diagram? Anyone? No? Free body diagram. Looks like this. If I draw us a car, yes, mate, you can. Yep. Here's my car, the bubble car. What forces are acting on that car? Right, please, talkers. If you're talking, I think you're not listening. Thank you. What forces are acting on this car? Gravity. Okay, let's draw gravity in there. Of course, it's a vector, so it has magnitude and direction. We'll give it F sub g. Yes. What else is Friction. Okay, so friction is okay, so say it's moving in this direction, V. Where's friction operating? Where is this force of friction? Up or something else? Opposite the direction of motion, isn't it? So friction is opposing that motion. And I'll draw it at the back of the car. You could just as easily draw it at the front of the car if you wanted to and say that's friction. But it doesn't matter where you draw the vector. Force of friction, F sub FR. What other forces? By my calculation, if this were true, if these were the net forces on that vehicle, the car's actually going to do this. It's going to accelerate in that direction, isn't it? But that's not true. It's going to continue on with this velocity. Therefore, those forces must be balanced somehow. What are those forces balanced with? Normal force. Is that what you're saying? Normal force. Yeah. What's the normal force? Where does that come from? Yeah, the ground pushing up on the car. It's equal and opposite to this force of gravity. Otherwise, the car would either start going up or it would start going down. What's this force then? If the car's moving with constant velocity, then there must be a force in this direction as well. Force of the wheels on the road. This is what's called a free body diagram. It shows all of the forces, and as a result, the net force is on some body, whatever that may be. This is a car with speed V, constant velocity. Here's a picture I'm going to talk about a little bit. This is that car on the banked curve. And there's actually there's only two forces acting on this car, but it looks like there's three forces drawn there, doesn't it? There's only two forces. What's the other force? Yeah, there's gravity. Oops. There's gravity kind of about the same length as Fn cos theta. What is the other force that's acting on this car at the moment? It's this one, isn't it? It's Fn. And what is it what are those other two forces there? Yes, it is. Yeah, exactly. It is. Well, actually, the car is accelerating in that direction. Now, I just want to point out, because this is a common misconception, and that is we have force of gravity here. Oh, hang on, the tablet's failing for some reason. Why is it doing that? Force of gravity. There's force of gravity here. It's exactly the same length as this Fn cos theta, which happens to be the vertical component of that normal force. You could actually take that normal force now and remove it, because I've got its components there. Okay, I could either have the normal force or I could have the components. What they've drawn there is both. They're showing you both. Okay, and when they're showing you both, just to make this image a little bit clearer. Now, what are the unbalanced forces? Well, this force here, force of gravity, which is equal to mg. This tablet's failing for some reason. I don't know why. Maybe the battery's flat. Force of gravity is equal to mg. This one's actually called the vertical component of the normal force, and it's equal to Fn cos theta. The unbalanced force is this Fn sine theta here, the normal force, the horizontal component of the normal force. It is responsible for the centripetal force. So Fc yes. Thank you, mate. Just on the pile there. Thank you. Centripetal force is provided by the horizontal component of the normal force. And I'll just highlight it there. This is it here. This is the guy. This is the one that provides all of that acceleration towards the center of some circular arc, or the circular arc that is the center of this banked curve. It's the only unbalanced force. Okay. And we saw the other day proof that this exists when the chap in that red Commodore was driving around the track, and he took his hands off the steering wheel. The tires, the friction between the tires and the road was no longer providing that centripetal acceleration. It was all Fn sine theta. Okay, it was all the horizontal component of that normal force that was providing that turn, that acceleration. Oh, that's right. I've got to show you something. There's one last thing for uniform circular motion. From this diagram here, you can see that Fn, F sub n cos theta, the vertical component of the normal force, is equal to mg. Some people are saying, what? Where's that come from? Is it? Have a look here. mg there, that's that vector there. Fn cos theta is exactly the same, but in the opposite direction. The magnitudes are the same, so I can equate those, even though their directions are different. Okay? Okay, yep. Now, in this situation, if the car is in, and I'll actually say it, if the car is in UCM, it has what? Constant speed and constant acceleration, doesn't it? Fn sine theta what can we then say about Fn sine theta? What is that equal to? If it provides the normal, if it provides that acceleration, if it's the only thing that's providing that force towards the center of that circular arc, then I can say that it equals mv squared on r, because that's what Fc equals. Okay? Then what if I do this? mg, okay, fn, mg cos theta, what do they do? Fn side theta equals mv squared on r. Mg on cos theta times sine theta have a look at what we're saying, that here cos theta, if I move the cos theta over here to the bottom line, I've set Fn equal to mg on cos theta, haven't I? All right, I'll just draw that in different color here. F sub n equals mg on cosine theta. Okay, that's the step in between. If that's what the normal force is equal to, can't I just sub that value in here? From that, I sub it into that for Fn, and I end up with, I've gone around about, I should have done them on top of each other. Sorry, the way I've done it. Mg cos theta times sine theta equals mv squared on r. What's sine theta on cos theta equal to? Yeah. Sine theta over cosine theta, mg. I'm just rearranging that mathematically. mv squared on r. I'll go down. This is much neater if I just go downward. Tan theta equals mv squared over mgr. Of course, I can just cancel the m's, and we're left with this uniform circular motion identity. Tan theta equals v squared over rg. Why they say rg, I don't know. Gr, doesn't matter. I just remember it as tan theta is equal to v squared on rg. Problem? So, just as a reminder for those people that maybe forgot, I hope you didn't forget, but 80 kilometres, I better make it white, 80 kilometres per hour divided by 3.6 will give us, by the book, 22 metres per second. Okay, so I've got my V, haven't I? What's my R? 250. Is that in standard units? Standard physics? Standard international units? Yes, it is. No reliance on friction to provide the force necessary. So what are we looking for? Yeah. Banking angle. It's banking angle, isn't it? So we could say tan theta. Remember, one note I wanted to make was that equals v squared on rg. Is that Always start with your formula when you're answering the questions. This is not optional. That's what I want you to do. Show the examiner, show the person marking the test, which is most of the time me, what you're going to use. Okay, I'm going to try and use this. It might not be right. You might not be able to use it, but at this stage, it looks like I can. So from that, I can go theta I can do that, can't I? 22.22 squared over 250 times 9.8. Whoops. Oh, yes, thank you. How much is it? Theta equals 11.4 degrees. It sounds reasonable, doesn't it? And by the book it says, yes, that's true. Who did get that answer? The question is, why do we divide this to get from kilometres an hour to metres per second? Why do we divide it by 3.6? Well, if you have 1 kilometre per hour, how do I change? Okay, that's the same as saying 1 kilometre divided by hours, isn't it? Yep. How do I change a kilometre to metres? Yeah. Times by 1,000. 1 kilometre to metres times 1,000. Hours. 60 by 60. Times 60. Whoops, 66. Hang on. 60 by 60. Isn't it? To seconds. Meters. Okay. That's so equal to, of course, 3.6 in the end, whether we divide or times. And the way to remember, because that's 3,600 over 1,000, right? The way to remember is kilometres per hour is always larger. The value is going to be larger than metres per second. Okay? In order to do 1 kilometre per hour, I don't have to do so many metres per second, so to speak. Okay? I'll just get rid of that. Was there another question there? No. There's another example here. Have a go at this, people.